What a magic. Here we go.
Hit record while I'm sharing. That's what's weird. But I don't trust that. Okay, there we go. So here's Nick's work. Lot of interesting things that he did in here as far as getting all this stuff. And then here's sort of the work he did with this. Screw the authors.
Yeah, I was at this point because I looked at because I was like I was going through this and I was like, how the heck I was doing? I did the quotient rule and then I did the product rule within the quotient rule. That's in the area where I circled in red, and I was just like, nope, that didn't work. So I looked in the book and see what they did, and I was like, all right, okay, I guess you can consider it a constant then. And I said, this is BS, and I pulled out the LV over CP like they said.
I feel like they skipped steps.
Well, let's take a look at what Nick did over here. Jim, you did another one that I want to take a look at. So let's just kind of evaluate how we're doing these things. I don't want you to be super intimidated, but you do kind of look at this. So he says, all right, so using the hint over here, right? Look at the derivative of this. Now, why is this not working? I might have to restart it. Come on. Epic pen. There we go.
Epic pen.
So what we have here is like, all right, so here's the hint. Take the derivative of this whole thing. So you're just going to do that. Now, when you do that, and I think this is kind of important, is you can take LV and CP out because you're taking the derivative of a constant. Okay? So that comes out in front. So, you know, what we're really saying is what we want to take is the derivative of W sub s over T. Now, you could do this thing called the quotient rule, which is fine, or you could make it the product rule, because for some of you who aren't, you know, the quotient rule is fine, but which is really just 1 over T times dWs plus W sub s over the derivative of 1 over T, which is negative 1 over T squared. Right? So that's kind of how that works.
Is that a minus sign?
Yeah, because remember, the derivative.
I'm sorry.
It's T to the minus 1, so you just drop it.
I'm sorry. It's 9 in the morning. I'm sorry.
No problem.
I'm in the morning here too, and I'm just fine.
You're a morning person. I am not.
Caffeine.
I know. I'm trying to wait for my caffeine. I do it during the midday.
Hold on. What did I do? This is weird. It's just Epic Pen opened twice. I need to get rid of that, and we'll just go back to this. There we go. Okay, so when I look through this, what I start to see are some. It gets confusing with the CP. Right? And the reason is the derivative needs to come out. So really, this is what you have to do. So most likely, Nick, it's in here, and I'm not going to go through it little by little in this, but you probably made an algebraic mistake. That's usually what happens. See, you get something that gets kind of weird.
Use the derivative calculator next time.
See, and then when you go into here, see, you have dLV over LV, and you're like, well, why did you call that the natural log? What did you really do is you were integrating it. And we're not asking you to integrate it at this point.
Oh, yeah.
So you did some good stuff, and truly, you know, it's good to see the effort. This is what I like to see from students. I don't necessarily need to see you in a homework assignment unless I'm just try this out. I don't need to see you being right. I need to see the kind of work that you're putting into. Okay, so let's go here, and I'm going to go to Jim's if you're all right with that.
Oh.
And one of the things about Jim's stuff that I like is he puts in, and this is a good thing. He just puts in here what he's doing. So given this, and then he's like, what am I supposed to prove here? So we have that. Then factors out that, and then we're just taking the derivative of this. Now he differentiates by parts, right? This, which is what we did before, okay? Which was what I showed you. So we're going to say at this point, all is good, okay? Everything's good within there. Now let's see what he did. He factored out a 1 over t, which is good because look what you have. You have LVCP over t, so he's factoring that out, and then this is what's left. Okay, then let's see what you did next.
I factored out a DT, and if I didn't have the hint that the book gave me, I probably would not have done that. That's where I got. That's where I, when I initially looked at it, I scratched my head. But once they gave me the hint, I knew to get rid of it.
Okay, so you're looking at, if you're looking at page 107 of the book, you're looking at 3.120. And that's
no,
what,
no, it's the hint that they said that DT over T is significantly less than WS over.
oh yeah. But at this point, right? If you look at 3.120, that's what this is. So this is 3.120.
Right.
So that's where that is, right? And then the reason that you do something like this is when you factor that out, you're going to get a ratio here, which that's a question. How does the saturation mixing ratio change with respect to temperature? See, I can look at this thing and say, well, I can ask that as a question. And then this is the ratio of W sub S over temperature. Now, when I take a look at this, what are we talking about? And this is something in science that we often call scaling. And this is a concept I'm going to introduce here because scaling is super important even in deriving the hydrostatic equation. Okay, now you know the hydrostatic equation, and we came up with the purpose for the hydrostatic equation. We said it was a upward pressure gradients balanced by gravity, blah, blah, blah. But the hydrostatic equation is actually a vertical momentum equation. When I use the term momentum equation, I'm talking about Newton's second law, F equals ma. And I'm looking at all the forces that act in the vertical. And we're going to see that gravity does, but so does the centrifugal force of the Earth. So does Coriolis force, points upward. There's an upward directed force, and you'll understand that later. So we have a lot of forces that go up and down in the air. But it's sort of like this. If I said, hey, look it, we need to talk about our debts. You owe me $1,000 for our gambling debt, and you owe me $2 when I bought you a coffee, and then you owe me 25 cents when I bought you a gumball. Okay? And I remember you lent me some money. You gave me like $700 to buy some furniture, and I think you bought me a cheeseburger. Okay? Now, when you're looking at the amounts of money that you owe, when I look at this, I'm like, you know what? Those things are really small. I'm not even going to consider that because when I look at what's the difference between us, it's really the big numbers that matter. So let me give you an example in the hydrostatic. If I look at force equals mass times acceleration, what are the and I'm going to sum up the forces. So what forces act up and down? Well, we know that there's gravity. We know that there's the vertical pressure gradient force. We know there's a Coriolis force. We know there might be the centrifugal force of the Earth. Lots of things that go up and down. But how big is the centrifugal force of a moving object from the Earth?
Small.
Really small. Coriolis force is like 10 to the minus fourth. Gravity is 10. It's a huge order of magnitude. So when I look at these forces, I go, I don't need this. They're small compared to these guys. They're way small. Now, if I were to look at this, I want to use something called an order of magnitude. Now, if you remember from Tuesday, I don't know if you heard Jim say, oh, it's an order of magnitude bigger, right? But when you use that term, an order of magnitude is a factor of 10 times. So orders of magnitude. This would be an order of magnitude of 10 to the third. This is an order of magnitude, when I round it, to 10 to the third. This is an order of magnitude of 10 to the 0th. Because they're really closer to 1 than they are to even to 10. So when I'm looking at this equation, I'm like, well, this order of magnitude is 10 to the third, this is 10 to the third, these are 10 to the first. So that's 3 orders of magnitude smaller, and they really don't make a big difference in the big picture. And when we do that in equations, we say that we are scaling the equations. The geostrophic wind is a scaled equation saying pressure gradient force, Coriolis force are the only 2 big forces playing a role. Okay? Does that make sense to you? I've given you this stuff to reflect. Does that make sense what I'm saying? Okay. All right, so give me the orders of magnitude of these 2 terms. Give me the order of magnitude of those 2 terms.
That's what they were getting at. Okay.
Is the dWs over dt going to be small because it's a little chunk?
Well,
Here's the thing that threw me, Paul. They said that as it relates to skew t log p.
Yeah, that was weird. But...
That was weird, but I just kind of took that as an assumption and went with it.
Yeah.
This is, okay, so this is a problem here. dw sub s over dt.
Right.
And then we have w sub s over t. And what did the book do? They went...
They gave the proposition that dt over t is significantly smaller than dw over ws.
Right? So what I'm saying is, remember, what is this all about? This is all about lifting a saturated parcel of air. So when I'm lifting air through the atmosphere, through a layer, how much does the temperature change within lifting the air?
Degrees?
In degrees.
Was it 1 degree per 800 millibars?
10 degrees.
Well, what's the dry adiabatic lapse rate?
-10?
It's 10 degrees Celsius per kilometer, right? So if I lifted a couple of kilometers, how much am I lifting it by? 40 degrees maybe?
Mm-hmm.
So we'd say, well, this number here up top, you know, we change by on the order of 40 degrees Kelvin. Or maybe 50 degrees Kelvin, right? That's what parcels are doing. And that's why it says, look at the skew T. Well, what are the temperature changes? But what is the temperature over? So this might be, I don't know, 50 kelvins over what's the actual absolute value? 300, 250? Let's even go 250. Because that's about the temperatures when you're somewhere below 0. So somewhere in there. So 50 over 250 is 1/5, which is about 0.2. So this order of magnitude, the scale of this term, it has about a 0.2 magnitude, which you could say is maybe 10 to the -1st. Now over here, what is the magnitude of these changes? Well, how much would the capacity change? Do you agree that these are going to be in, like, when I'm lifting the air till when it's saturated, let's say that it has 20 grams per kilogram to start, right? But how much am I changing? I'm condensing almost all the water vapor out. So maybe I'm taking out 19 grams of vapor out. But what was WS to begin with? 20. Well, what's 19 divided by 20? That's an order of magnitude of 1. So the ratio of the temperature change to the temperature is much smaller than the ratio of the capacity change to the capacity. What we're really saying is that dt is much less than t. Let's even go much less. Whereas dw sub s is about the same magnitude as w sub s. So when all is said and done, this is where they show in the book dt over t is a lot less than dw sub s over w sub s.
Someone tell me what page we're looking at.
We're on page 107.
Thank you.
Because, and we just looked at, and it's, we can see that easily with the
skew T or a thermodynamic diagram.
yeah.
But the point is, when I'm lifting parcels, right, we know that we've got about 20, at most, even on a high day, we have about 20 grams of water vapor in the air. When the air is saturated, we still have 20 grams to start. And then we lift it, and some of that condenses out, and now we have 1 left. And so we took out 19. But 19 over 20 is about 1. Because what we're saying is that the order of magnitude of the change in the capacity is on the same approximate scale as the capacity itself. But the change in temperature is much less than the actual temperature because I have to use kelvins. So even if I drop the temperature by 50 degrees, which is a pretty sizable partial drop, it's still divided by about 250, which is still going to be considerably smaller. Maybe an order of magnitude 5, 6, 7, 8 times smaller. So then, if that's the case, then they go, well, 3.121, they go dw sub s dt is a lot bigger than w sub s over t. Now, how do they get to that reasoning? Again, the change in capacity, dw sub s, and w sub s are about the same. So then you're kind of assuming the numerator is about the same order of magnitude. But the change in the temperature is a lot smaller than the actual temperature. Therefore, the ratio is a lot bigger. Are you guys seeing that in the book on equation 3.121?
Yeah.
Okay. So now you change the page, you turn the page, and then we can go back to, actually, let's go here. Let's go to gems. So he says by induction. So, and really what I want you to learn, and this is where I think, to be honest with you guys, when I look at science people, and I think of science teachers, do you know what I think their biggest weakness is?
Not explaining everything.
They can't explain it. You know why? Because they're not really at that level 3 understanding of communicating it.
It's also, with respect to the book, that knowledge has been lost because the original paper was probably written in the 20s and the 30s about this.
Yes. So this is sort of a summary statement, and a lot of times the book skips over, so the authors suck, is what you. And by the way, in problems, I think a lot of times graduate students do the problems.
Yeah.
They're the ones who write the solutions to it. But Again, what I want you to do is we're looking at the ratio of the change in the capacity to the change in the temperature, capital T, is much larger than W sub S, the capacity, to the actual temperature. So we're saying these are about the same. This is much smaller than that, which means this is true. And when it says much larger,
In the eye of the beholder.
But here's what you could think, right? If I take a parcel and I'm not going the entire way, if I'm just looking at the derivative, a small, infinitely small amount, temperature is still going to be really high. But then we rewrite with the proposition, which is what we had here, and then we say, okay, dt over dt goes away, and I've got this. And then he goes, this is the left-hand side of our assumption, which he had up in the beginning. Therefore, the assumption is valid. Underlines it, exclamation point, me likey the way he did this, right? You can tell Jim's a good scientist because this is outstanding work, right? This actually, not only is this done well, but it has meaning in the future to look at. I can go back and see all these things. So I'm kind of happy with that. So what that means now, okay, first of all, before we go on, is there any question that you have over this?
Makes enough sense, I guess.
Right? I mean, this is tough. But again, the key thing is to be able to communicate what this means and to think through what it is and then to speak it out loud. And now I'm not saying that all teachers do this, but I know a lot of teachers would go, and then dW sub S over dt is a lot bigger than W sub S over T. And then they just keep going on. And most students, right, most students would sit there and say, what? I don't know why that is, but I'm not going to say anything in class.
Yeah.
And so there's no learning. You're just doing it.
That's the problem that I'm having in dynamics right now is he goes through all these proofs, but he just like says it. And like when we get to the problems, I'm like, okay, how do I even start this? Like we haven't even begun. Like I feel like in class, I'm like, okay, it makes sense because he's saying it makes sense. But then when I actually step back and reflect, I'm like, what the fuck did I learn?
And so what you do is students will then just sort of memorize the order and are able to do it. And then there are students who are good science students. They're able to do that without thought. They don't challenge it. They just go, yeah, that's right. And that's fine for most students in college. They accept what it is, and they're like, I get it enough that I can do it. But they don't really know it. And I don't like that idea. All right, so now we go back to page, where were we? 85. And now on page 85, we go back here. Where's my epic pen? There we go. And we go to we had this, so I'm just going to redo it a little bit. LV over CPT times dW sub S is equal to d theta over theta. Then we said, okay, now I'm just going to put minus d of all of this equals d theta over theta. So it's this tricky step. If you recall, the reason we did that is because we needed to find a way to integrate this. And by creating this approximate assumption, so this is approximate. by creating that approximate assumption, now this becomes really easy to integrate. So what do we need to do? We need to integrate both sides. Okay, I'm going to go ahead and just remove the yellow arrows so that I don't get they're out of my way. And in integrating this, oops, I can put the integration here, and I can put the integration there. Now, what am I integrating on the right side? I'm starting at some value theta to this new value theta E. Because that's what I'm trying to define. What is equivalent potential temperature? And if you recall, equivalent potential temperature is the potential temperature the air will become when all the water vapor has condensed out. So when so all the water vapor has condensed. Now, when all the water vapor condensed, what is W? If all the water vapor is condensed.
0.
W would have to be 0.
Yeah.
But the only way that W is 0 is if W sub S is 0. Now, you should know, I would hope that you know, that when I look at a chart like this, and I plot W, and I plot W sub S versus temperature, it's exponential, right? So when does W sub S become 0?
At T equals 0.
At absolute 0. Can we go to absolute 0?
No.
No.
Doesn't really matter. We're saying is that there's this theoretical limit. It's like saying, where does the pressure go to 0 in the atmosphere? And that would be infinitely high. There's nothing above me when I'm infinitely far from the Earth. It's all about limits. So we know that that's the case. But so the question is, when I'm at theta E, what's W sub S? This whole term becomes 0. Right? And then what would this term be at theta? And the answer would be LV WS over CPT. Right? I'm integrating limits. So I'm saying this has got some value. Now we know the LV and CP are constant, so that's not a big deal. But when the air becomes saturated for the first time, there is some capacity. And there is some temperature where this is happening. You're not the LCL. And I have a theta at that point. Theta has not changed from the ground to the LCL, right? It's constant. It's an isentropic ascent. And then I go to theta E where it goes to 0. Now, when I do this integration, this is really simple. It's just this value, this minus this, but there's a minus sign. So you could have, watch carefully, you could have gone plus, and then switch the limits of integration.
That upper limit is 0?
The other, yeah, the upper limit 0. But if I put a plus in there, anytime I take a plus or a minus in the integration, I'm flipping the limits of integration. It's this minus that or that minus this. So the left-hand side just becomes LV W sub S over CP T. What does the right side become? What's the integration?
Negative theta, 1 over theta squared.
No, integrate.
Log theta.
Evaluated from theta to theta E. which by rules of logs becomes the natural log of theta e minus the natural log of theta equals LV WS over CPT. And I'm going to go up here just because it's easier. And I'm going to say this becomes LV WS CPT plus natural log of theta equals the natural log of theta E. Actually, you know what? I think this is, let me undo this. Please forgive me. I think this is a better way to explain what I'm doing over here. There's another rule of logs.
Divide them.
Theta E all over the natural log of theta. Multiply through, so I get natural log of theta times LV WS over CPT equals natural log of theta E. And then now I can take the anti-log and I get theta 2, the LV WS over CPT equals theta E. Okay.
So once you take the natural log of both of those out, you just end up with theta EWS over CPT equals theta E?
No, he's exponing both sides.
Yeah. E to both sides. So
Okay. E to both sides.
they use EXP. I'm just putting it up in there.
And EXP is multiplied by E, right?
Euler's number, yes.
Okay.
Yeah.
Okay. That was one thing I was pretty sure of, but I wasn't like 100%. So.
Okay. What? Oh boy. You know what? I'm seeing something. Here, while I'm looking for something else, let's try one. Use this a diagram. Temperature is 20 degrees C. Pressure is 1,000 millibars. Dew point is 10 degrees C. What's theta and what's theta E? And I don't want you to use, I want you to use the chart to find theta, but I want you to use this formula to find theta E.
How much was pressure? I can't read that.
Millibars.
1,000 millibars.
Okay, that's 1,000 millibars.
Oh no, no, no. Oh, here we go. How you guys coming on that?
Hmm.
Oh my gosh. Hey, Jim,
Sir,
do you have this book?
is that the first edition?
Edition.
Yes, I do. It's much better than the second.
Turn to page 76.
So this is a case where the first edition book is actually better than the second edition?
Well, they took something out in here.
They've done that in other problems too.
Does anybody else have the first edition of this book?
Only when I found the second edition.
Well, then we have something really important to do. And I started freaking about it because I know I have these in my notes, but my notebook is in my office. So that doesn't do me any good.
If you look at page 72, how they did that problem is different than what was in the second edition.
Which problem? Pages don't match.
I think it's 319 where we're calculating TV.
Okay.
The derivation is different between the first and second editions.
Okay, well, anyway, did you guys get that? So what did you have to do first of all with this information?
Oh, I forget.
You needed to find the LCL, right? You have to do that. And we should know that theta, because it's 293, right?
Mm-hmm.
So, and when we're at the LCL, what's the temperature at the LCL?
Fucking course.
What's your temperature at the LCL?
Every time I need to actually hear.
Which temperature?
The temperature of the parcel at the LCL. Because you need to have that information right there. No.
I didn't hear what you said. My internet went out.
Just what's the temperature at the LCL?
I forget how to do it. I'm going to be honest with you.
Oh,
I have the thing in front of me and I tried to figure it out and I don't remember.
that's it. Everybody's getting enough.
Theta.
Okay, so here, right? I'm gonna have to erase all this, but
Okay.
that's okay. I don't think I need to have this.
So 20.
So I'm at temperatures 20, and then I go up a dry adiabatic from there. It's not.
Mhm.
Whoops. No, let
Let's
me try to be a little bit more specific.
6 degrees.
And then the dew point is
Yeah.
10, which means that so the temperature is what? What I would say maybe 7.
No. 6.
Did you say 6?
7 or 8, yeah.
I would probably go more 7. 7 Celsius. So the temperature is not 7 Celsius, but
299 Kelvin.
what?
280.
Or 280 Kelvin. Duh.
380. Okay, now W sub S should be W because it's the same. So that would be W sub S is it 8 grams per kilogram? Yes or no?
Yes.
But that's not what you use. What is it that you use?
8,000, or yeah, kilograms per.
Kilograms per kilogram, because there's no unit. So you're just putting in W is 0.008. Now when you look at the equation, so now you need LV times W sub S divided by CP T. So we have 1,004 times 0.008 divided by, what is it? I don't know the number offhand. 4,128 joules per kilogram.
You just want
So
1,000 more.
it's in your appendix. So that's the number you need to know.
He just said 1,004.
EP is 1,004.
Right.
But what's the latent heat of vaporization?
2.5
It's
times
2.50 times 10 to the 6.
6.
2.50 times 10 to the 6 joules per kilogram. I'm going to ignore all those, okay? For this sake. If you did it in my test, I would take off points. Times 0.008 divided by 1,004 times 280. And then what do you get with that? What is that number?
Really, really quickly, because I think I just sort of missed this. How do you get T equals 280K? I thought it was 293.
No. Theta is 293. But you're asking me the temperature at the LCL. This is where you're starting.
Okay. It's not the, okay. I get it.
I get seven.
This is where you start to get moisture out.
I got 7.11 times 10 to the minus second.
7.11 times 10 to the minus 2.
Right.
So then I take theta, which was 293, to the exponent 7.11 times 10 to the minus 2.
I get 314.6.
You get that number? Everybody confirm that number using your calculator? Now we know that it's the value of the wet adiabat, which you're basically on the wet adiabat, which is 314.5. So now you know a better way to do that. You just got to remember that this is temperature at the LCO. That's when it first starts happening.
That's
Does that make
pretty
sense?
cool. It lines up on the graph perfectly.
Well, the graph is drawn so as to actually make this work. You know what's hilarious is I started this graph. I had a student when I was in 1987 or 88, the late 80s. And she was a graphic design major. This is before computers. There was no thermodynamic diagram that was good. I had one in a book, and she took them off, and I don't even know how she did it, but she created all these lines individually. And she just took the estimation off a graph, so that's how I could take it apart and do this. And she's done a really good job. They're really very accurate to what we want. So does that make sense? Now let's do this. Let's talk about this for a second. What is the wet adiabatic lapse rate?
5?
No. Remember we said in class it's the dry minus the amount of latent heat.
Oh.
But you also agree that the adiabatic lapse rate, dry adiabatic, looks like this. What does the wet adiabatic lapse rate look like?
Curves.
It curves. So do you understand that it's continuously changing?
Mm-hmm.
Well, we often said, and I just went through this in my one class, I said this is dependent upon how much water vapor condenses, delta W, which is dependent upon how much have to condense, which is really equal to the amount of temperature change and the temperature where that change takes place. Obviously, at warmer temperatures, the line is
More vertical.
smaller lapse rate. And as I get colder, I get a larger lapse rate. It approaches 10. Well, how do I know what this value is going to be? So this is what the book doesn't have, and the old book does, is how do I derive the wet adiabatic lapse rate? So I'm going to say, how do I derive the wet adiabatic lapse rate?
I'm going to cheat.
Okay, and I'm going to use this in the book. And I'm going to say the first thing I do is dq equals cp dt plus gdz. And what is this? What is
Alpha
this?
dp, or negative alpha dp.
Well, yeah, this is alpha dp, but what is this whole equation?
First law?
First law.
It's the first law. Why do I want the gdz instead of alpha dp?
Did you want it to depend on height?
Because I'm going to be dealing with the lapse rate, which is dt over dz. But it's a little bit different. Now remember, what is the heat in this equation?
Normally it's 0, right? Because we do it adiabatically.
But that's dry adiabatic. This is now wet adiabatic.
Latent heat.
So it is the latent heat, right? As the capacity is changing, it's how much is condensing. Remember, W and W sub S are the same when the air is saturated. Equals Cp dt plus gdz. Then we want to rearrange terms. So I'm going to do this. I'm going to take dz. I'm going to take Cp. So now what do I have? Let's look at what I have after I do all that stuff. I have minus L over Cp. And I guess, to keep our consistency, we should say LV, latent heat of vaporization, dW sub S over dZ equals dt dz plus G over Cp. And then I'm going to solve for dt dz. Minus what? What does this become? See, it would be minus G over Cp, but that's the dry adiabatic lapse rate.
Mm-hmm.
Okay? But this is where it gets kind of weird. You guys see that? Because what is this? What's that?
Partial?
No, they're D's. I'm sorry, it's just messy. What is that? Oh my gosh, how many times do I have to do this?
That's a question.
What's the question?
How does the
Saturation change over.
With height.
So, do you know any relationship of how the saturation mixing ratio changes with respect to height?
no?
Yes, don't we?
Why would we? You know it changes with respect to temperature, but you don't know how it changes with respect to height, do you?
No.
You got to know what the temperature is doing. So this makes no sense. I don't know what that is. But do you agree that I can do this? Now, what are these things? What are those things?
Questions that we know.
Questions that you know. How does the capacity change with respect to temperature? Well, we know that's an exponential relationship. How does the temperature change with respect to height is called the what?
Dry adiabatic lapse rate.
No. This is just how the temperature changes with height. That's just a lapse rate. But that's over here, isn't it? So what I need to do is I need to bring it over on the other side. I need to say dt dz plus LV over CP dW sub S dt times dt dz.
We're gonna factor it out, I'm guessing.
And then factor it out. And then we say, all right, so dt dz is equal to 1 plus LV CP dW sub S dt equals the dry adiabatic lapse rate. Then I take dt dz equals the dry adiabatic lapse rate all over 1 plus LVCP dW dt. And therefore we say bless you. So we are basically saying we're going to define this lapse rate to be this. Now you might ask, where did the minus go? I think, that's fine.
You got is that a triple equal?
Yes,
Okay.
we're defining it as.
Okay, I'm just making sure.
But so we need to say, okay, well, let's take a look at what's really going on. What is the value in the denominator? First of all, what's the value in here? What's the value there? That's a number, right? It's a positive number.
Positive number.
What's the value here?
Negative?
Right, because I'm going higher, the temperature is changing. So here's the problem. How does the capacity change with respect to temperature? The value of that is negative.
Okay.
It gets smaller.
Okay.
So what's the value? No, I'm sorry. This is what? This has got to be positive, isn't it? This right here has to be positive. Why? Because as the temperature goes up, what is the capacity doing?
Also going up.
That's a positive value.
Right.
If the temperature is going down, that's a negative dT, and dW sub s is negative, so that becomes a negative negative. So
Positive.
in the bottom, the number is going to be greater than 1.
So the product of those two is assumed to be greater than 1, therefore the denominator will be negative.
No, this is positive. Both of these are positives, right? So that means the denominator, which is 1 plus a positive number, this is a value, and let's do it this way, okay?
Oh.
This is a value greater than 1. Well, if that's the case, what is the wet adiabatic lapse rate compared to the dry?
Smaller.
Right? So we know that the wet adiabatic lapse rate is less than the dry adiabatic lapse rate by some amount. The funny thing is, it's not really, like I always said this, and really it's going to be not a sum, but a product.
Mm-hmm.
It's going to be a percentage of it. Well, what's going to make this number smaller? In other words, more this way. What's going to make it more that way? This is smaller.
The bigger the denominator?
The bigger the denominator. Well, these two are set. The only thing that can happen is I have a greater capacity change with respect to temperature, which should make sense because the relationship of this graph
It's exponential.
is exponential.
Mm.
So the further I am to the right in this graph, in other words, at higher temperatures, the capacity changes by more because if it's exponential. And the more that it changes, the bigger the denominator becomes, the smaller gamma sub W. So it's not product-y, it's a percentage. It's a division problem. It's quotient-y or whatever.
Question?
It's summy. It's not summy, it's quotient-y. Yeah, go ahead, Jim.
On the left, the bottom left, you bring in another dt over dz. Where did that come from?
Here, dw sub s dz, and then I just divided both sides.
I see what you're doing. I see what you're doing. You're multiplying by 1.
I've got it twice, I need to put it on the other
I
side.
see. Okay, I see what you're doing. Duh. You're just multiplying by 1. Got it.
Yeah, this is really a confusing but really cool explanation of what this is. And the reason I teach this concept where it's dependent upon the temperature change, what the temperature is and the temperature change is all based on this graph, but this is the actual mathematics that work it out. So let's say,
what's that last term in the top? Gamma W equals gamma D plus.
Where? In here?
In the middle.
Blue
Yeah, in the middle. Up in the middle, the blue.
Oh, LH. Gamma W equals gamma D plus latent heat. That's just what I was talking about. I talked about it in being this is dependent upon, well, it is dependent upon these things. And the reason it's dependent upon this graph is because of this term here, which is really the key. How much does the capacity change? If it were linear, it wouldn't matter what the temperature is, but it's not linear, it's exponential. So let's try an example here. Let's go to the example that we just used. What was W sub s in the example we just used?
.008.
0.008. Okay? Kilograms per kilogram. Just to remember. Now, you don't have to write that because it's unitless. The mixing ratio is a unitless thing. And we're at about 900 millibars, right? Someplace where's the LCL? Take that parcel, wet adiabatically, to 800 millibars. What is W sub s? So this was at the LCL. Now lift the parcel to 800 millibars. What did W sub s become on that chart? Can you do that? Do you know how to do that? Do you guys know what I'm talking about?
Yeah. Hold on.
0.006, I'm thinking.
0.006. Is that what you're saying? That seems about right. I've condensed out 2 grams of water vapor. What's the temperature of the parcel at 800 millibars?
Say about 2 degrees Celsius.
Okay. Now, you should be able to tell me what was the wet adiabatic lapse rate in that layer. You know LV, you know CP, you know DW sub S was 0.002, and you know DT was 5. So plug that in, and what's gamma sub D?
Is it the?
That's the dry adiabatic lapse rate.
Sorry, it's the 9.81, something
Not
like
just
that.
9.8.
Yeah.
So 9.8 degrees per kilometer. Right? Just so you know, we usually use 10 in the intro class. Now we'll use 9.8. So plug that in and tell me what the wet adiabatic lapse rate is in that little bit of a layer. At least an average.
Over 100? No. Is that LV or LD?
You guys have an answer yet?
Just writing down all the variables I need to make sure I'm keeping track.
I somehow keep putting in the wrong number. My fingers are a little clumsy in the morning.
2.
Yeah, I get 5.00998.
What's the unit?
I haven't gone that far.
Well, should be.
Kelvin?
This is lapse rate.
Oh yeah.
No, it's this. And if you work these units out, they should all go away because LV and CP are the same except for the unit of temperature that LV has. It doesn't, and CP has per Kelvin.
Mm-hmm.
So the Kelvins go away. These, everything else goes away. There's nothing. The denominator should be no unit. The top is a unit of degrees Celsius per kilometer.
Okay.
And do you understand that a degree Celsius per kilometer is a Kelvin per kilometer?
Yeah.
So if you went Kelvin per kilometer, that's fine too. Did everybody else concur with this?
No, but I'm double checking the math real quick just to see if I did that right.
Same here.
I got something like 4.9, so it's close.
What did you use for your DWS?
Whoops.
0.002.
Okay.
Over 5.
I would go LD CP dW sub S over dt, and I would just go, what is this, 2.5 times
10 to the 6.
6.
6 over 1,000.
Again, I'm gonna lose the units times 0.002
Over
divided
5.
by 5.
Right.
And did you get 5?
All right, there we go.
Add it. Well, you have to add 1, and then put it
Oh,
over.
yeah. Right.
And then put it over, divided by the lapse
Then
rate.
you have to do 1 plus whatever that number is.
Mm-hmm.
So you have to put it in there. Everybody okay with that?
I think so. So just to make sure I got the formula right and to reiterate it once for memory, it's the dry adiabatic lapse rate over 1 plus LV over CP times DWS over DT.
Correct.
All right. Oh, okay. That's
So James, think back a year and a half ago. Would you ever believe you were doing this?
honestly, no. It's I'm certainly gonna have to go over this again to make sure it sticks, but man, it's I have to say the way you approach a new class certainly helps you with how you deal with the new information. Like the problem last night specifically that I did with my dad, because he's great and he wants to be involved in my learning process. It took us a little while to figure out what we were doing, but when we finished it, it was great. I couldn't help it, like just absolutely be happy that I got that.
That's cool. Do me one more favor while I'm getting coffee. Take the same problem, take the wet adiabatic lapse rate from 500 to 400 millibars. So take the parcel of 500, and there you're going to have a W sub S and a temperature. And then go to 400 millibars, you'll have another W sub S and a different temperature. And calculate the lapse rate, the average lapse rate from 5 to 400.
What, Android? Oh, I assume so.
Just the wet. So you know what is it when you get up there?
Oh, well, yeah, the dry is always constant.
Ellison, you still use 2.5 times 10 to the 6 as your latent heat, right?
Yeah.
Okay.
I think you're just a little off because I didn't round it all. I just
Yeah.
used the 0.9960152936255 plus 1, and then I did that 10 divided by that number.
Oh, you did 10.
Hmm.
Okay, that's probably where it was. Yeah.
What did you
I-
use?
I used the 9.81. So I mean, I was like, it's pretty much close. There must have been something rounding there that we did different. So.
Yeah, I see where you get the 4.9.
Lab thermodynamics diagram. I really need to find a better resolution version of this. Hold on.
Have you guys seen these new arc lighting candles?
Oh, I love that.
It's like no more. It's like you just don't have to worry about it. Kind of cool.
Yeah, I want one.
You don't have to worry about. I don't know how it works. It's just arc of electricity.
Yeah, it's like a taser, a mini taser.
Oh. Well, I'll try not to phase myself. Do you guys get that one?
I'm still doing it.
So you would say the temperature is what, like negative 18 to negative 33, 32?
Can you show on the thing what you're doing so I can make sure I'm doing it right?
Well,
The thing.
I mean, I could. All right, I'll have to lose everything. But watch, right? Here's the parcel. The parcel was on the 3, you remember it was the 315?
Yeah.
So it's following up here. So at 500 millibars, it's here. Oops, here. So that's negative 18. And then up there at 400 millibars, it's negative 32. So dt
Yeah.
would be 14. And then W sub S over there is what? It's like 1.8.
Mm-hmm.
And then up there, it's 0.6 maybe.
Mm-hmm.
So you're looking at so dW sub S is 1.8. And then you just plug those same numbers in. What did you get?
Wait, why would it be 1.8?
Yeah,
1.2.
1, 2.
Okay, yeah, that makes more sense. I have to admit, sometimes I still struggle to tell all the types of different lines apart on one of these diagrams.
Practice.
I get 8.076.
From 500 to 400 millibars. And you said 8.076, or
Yeah.
8.08 degrees per kilometer. So that's sizably different, right?
Yeah.
Now look at the temperatures. Is that what you should be using? What temperature was it? Negative 18?
Mm-hmm.
If it were negative 18, then would the water vapor be condensing? You should be using latent heat of sublimation. Because the negative 18, it's not liquid water. It's coming out of the air through deposition. So you should use instead, what if you, here, go ahead and do the same problem, but this, instead of using 2.5, use 2.85 times 10 to the 6. 2.85 is the latent heat of sublimation.
I get 7.88.
So it's a little bit different, right?
Mm-hmm.
You're actually do you understand that that would make the air actually a little bit more unstable with ice instead of water? It's kind of cool, isn't it?
Oh.
Lots of little things. Now, if you go up really high, what does W sub S become?
0.
Really small, right? So if it's coming closer to 0.1 and under 0.1, this is becoming smaller and smaller and smaller. And the wet adiabatic lapse rate is becoming more the dry adiabatic lapse rate. So when I look at this chart, look at these lines, the wet adiabats over here. They're almost dry adiabatic now.
Mm-hmm.
But when I'm way over here, I still have a ton of latent heat.
So that kind of makes sense, because the colder it gets, the less capacity the air has for moisture. So the closer the moist lapse rate becomes to the dry lapse rate.
Yep. So let's just go crazy in the summer just for a second. Let's take 30 degrees, which is what, 86 degrees? But let's take it as a really high dew point. Let's take dew points of 23 degrees maybe, in the low 70s. So do you see there's the LCL? Everybody okay with that?
Yep.
Nope.
So let's go from there, where the temperature is what? Temperature is 21. And what's the saturation mixing ratio? 18, let's say?
18.
Don't forget, it's 0.018, right? And let's go up wet adiabatically to 800 millibars. And now W sub S is 15. And the temperature is now what, 16?
Mm-hmm.
So now we have dt is 5, dw sub s is big now, right? It's 3.
Oh, yeah, 3.
So what would that wet adiabatic lapse rate be?
Uh, 3.9.
3.9. That's pretty crazy. So, remember we talked about tornadoes? Why do we want tornadoes? We want the tornadoes when the LCL is low.
Mm-hmm.
So if the LCL is low, that means, what does that mean? Like if I asked you this on a test, and I said, okay, meteorologist, why do we want the LCL to be low for tornadoes?
Because evaporation underneath a high storm.
That can be partly the case. That is partly the case. That certainly will, okay, so what that says to me though, Allison, is it doesn't mean that we can't get stretching of vorticity. It just means that cold air may undercut the mesocyclone. So that's not necessarily always the case, but certainly part of it. But when the LCL is low, what else does that mean? It means the air is saturated at high temperatures. We want the air to saturate at high temperatures. Because if we're saturated at high temperatures, what will that imply? Right?
Mm-hmm.
If I saturate the air at high temperatures, the wet adiabatic lapse rate is going to be small. What is instability?
It's the ability for air to cool on its own without lift, right, or to rise without lift.
Yeah, but that's, remember how I always say this? What is instability? Instability is
A race between the environment and the air to get cold?
Is a race between the environment and the parson to get cold. That we want the environment to win. Okay? The dry adiabatic lapse rate is a very fast rate of cooling. But if I get it saturated at high temperatures, this becomes a very small, slow rate of cooling, which means I can get instability, I can get CAPE very rapidly. And it's the low level CAPE that matters the most. How much low level CAPE? Because what do I really want to do is I want to take vorticity and stretch it. Low level vorticity and stretch it. And when I've got low LCLs, those parcels are going to accelerate within the cloud very rapidly, and I'll intensify the rotation. And that's all because of this wet adiabatic lapse rate, which is all because of that formula, which is, 1 plus LV dP dW sub S dt. And I think that, folks, is an important section to know, but your book doesn't even have it. I don't know why they took that out. But I think it's important that you get the concept in this thing in there. Okay, turn to page 88.
Yay. The stuff I need to do.
Static stability. Okay. Now, if you look at figure 3.12, we are going to define static stability. So let's do this. Whenever you see the word static for stability, you are talking about lapse rates. Just so you know. If I say something is stable or unstable, we're talking about particles. Static stability refers to lapse rates. So if I said to you, the atmosphere has low static stability, that means the environment is cooling off quickly. So if you look at 312, they have positive static stability and negative static stability. How often do you get negative static stability? That's figure B.
An inversion?
No. That's the lapse rate's greater than the dry adiabatic lapse rate.
Oh.
How often is the atmosphere lapse rate greater than the dry adiabatic lapse rate?
Very, very rarely.
Where do we get that?
Oh, I remember you mentioning this in that class. That
Yeah, you remember where we get lapse rates that are greater than 10?
In the desert?
No.
No, mountainous forcing.
No.
No.
You see, here's two things that are happening. Do you understand that a lapse rate that's dry adiabatic means the theta dz is equal to 0? Right? How does theta change with respect to height? It doesn't. When I have the ground and I'm mixing the atmosphere with turbulent eddies,
Okay. Oh, the boundary layer.
In the boundary layer, I'm redistributing heat. That is what I'm attempting to do. So in the boundary layer, the atmosphere is dry adiabatic, or at least approaching dry adiabatic.
It's well mixed.
It's well mixed, okay? When I lift air, if you recall, what happens when air ascends is the lapse rate increases. But it always tries to approach 10 degrees Celsius per kilometer. It's very hard to get past that. The only time that's going to be true is if you look at soundings, you will see this. You have something in a sounding where you'll often see this. You'll see the temperature go way super adiabatic in the molecular boundary layer. And since you're putting a lot of heat into that molecular boundary layer and you're mixing it up just a little bit, you actually have what we call the skin temperature. So your skin temperature tends to be hot. So if you actually measured even 2 meters above the ground, that tends to be a little bit hotter than dry adiabatic. So your soundings usually have a little bit of a dry, what we call super adiabatic lapse rate near the surface, and very small amount. But this is why we don't often want to use SB cape, because surface-based cape will be too much. What we want to use is ML cape, which mixes that atmosphere, and we don't get that incredibly unstable air. But obviously near the ground, you see little things like leaves or something flying up on a hot day. It tends to go up pretty rapidly, but that's only a few meters. The only time that you would see that super adiabatic is if I'm bringing in, I've got warm water with super cold air. Then my lapse rates get super adiabatic. So in a sea breeze, this becomes really steep lapse rates.
Lake breeze too?
Not in a lake breeze. This is actually synoptic scale cold air moving over warm water, where the air is being heated from the water, and then it just drops off really rapidly. So
Okay.
in a strong cold advection regime over water, and you give the water a little bit of time to heat the lowest part of the atmosphere. Because remember, the boundary layer is still being mixed here from the warm water, but it's only maybe a couple hundred meters up.
So what we,
The air up here can go super adiabatic.
so kind of what we're seeing right now with cold air mass moving over warm Lake Michigan.
Yes, it's got to be really cold air.
So
Then you get these super adiabatic lapse rates.
So the only places it occurs is really close to the surface and when a sea breeze comes in.
Not a sea breeze. Okay.
Or cold air over warm water.
Let's talk about this. A sea breeze is generated by differential heating.
Yeah.
Okay. This is saying, here's Lake Michigan. So here's Illinois, right? There's Lake Michigan. And what we're saying is, I've got very cold air advecting over the lake. The path that it takes, what do you call that? The path over water is called the what?
Fetch.
It's called the fetch. So if the fetches are right, you're giving that really cold air chance to be heated by conduction from the warm water. It's going to conduct and heat the layer in the planetary boundary layer, which is over water, is only a couple hundred meters thick. So in that environment over the lake, you might be looking at well-mixed warm air, 200 meters thick, and let's say the temperature goes up to 12 degrees Celsius. It's very warm water. But the air temperature up at a kilometer might be -10. Now we've got 22 degrees Celsius per kilometer. Well, that's going to cause any sort of lifting, any mechanism, especially if it's saturated, to rapidly grow. And remember, the purpose of instability is to make the air more stable. Because what is instability actually doing? It's redistributing heat vertically, right? What do we call the redistribution of heat through fluid motions?
Convection.
That's convection, right? And to a meteorologist, that's three-dimensional to a physicist. But to a meteorologist, convection is always up and down. And what do we call horizontal mixing?
Advection.
That's advection. So we are more concerned with convection, which redistributes heat. In a thunderstorm, what is a thunderstorm in my book? Warm air
Rising?
and cold air sinks. So I'm taking warm air down here, making it go up, replacing it with cooler air. I'm stabilizing the air. I am increasing the static stability of the atmosphere through thunderstorms. So I wouldn't get negative static stability very often. Most of the time I get minimal static stability. And that's kind of what we're talking about.
So thunderstorms increase static stability by restoring the balance to the world effectively.
Correct. And the atmosphere is always trying to get to a statically stable environment. And this, of course, is with dry processes. Obviously, we know that wet processes are going to be more difficult. Okay, so now we go back to the book for a second. And we say, okay, well, if I have a parcel now in this environment, so here's my parcel, what is the force acting on the parcel?
Pressure?
Well, it truly is a pressure gradient, right? But what they have in the book is they go F is equal to F equals ma. You agree that this is density per cubic meter.
Mm-hmm.
So that would be specific volume. And this becomes mass. And then it's the difference in the density. Here is what, when you see this sign, oftentimes you'll call this the perturbation. And this is like the environment. So you will often see P prime, you'll call that the perturbation pressure. It's basically, you're thinking of a parcel. So if you look at this, there's going to be the parcel in there. Now, look at this next equation on top of page 89.
What was the first P called again?
Just the environmental.
Environmental.
That's the environment. That's the actual density. The perturbation is always the parcel. It's always the disturbance. It's always the cloud, whatever you want to say.
1040.
Yes, I want to look at one thing left. Okay, so look over there. You have, if I took this,
Another question.
how does
The height change with temperature or time? Time.
with time, right? The height change. Now remember, this is the same thing as dx dt, which is, how would you call dx dt? How does your what change?
Distance.
No, dx is a distance. What is changing?
Location.
Your location changes. The change in location is a distance. This is a change in location. It is not a change in distance. So this is the location. And how does my location change in time? That's a speed, right? That's a velocity. So this really is your height. That's your vertical location. So really, if you want to look at this, this is how does your vertical location change with respect to time? That's a vertical velocity. So what do we call a vertical velocity? What's the letter? Remember vertical velocity?
W?
Oh.
Right? UVW.
Oh.
Vertical velocity. Okay. Now, what if I did this? dW dt is a what?
Vertical acceleration?
That's a vertical acceleration, isn't it? Well, that means I have to take the derivative with respect to time of a derivative. The derivative of a derivative is what we call a second derivative. And so the notation we do is this. That is the notation of a second derivative. And what we do, and I'm going to let you read through this and we'll go through it on next week, but I want to get to 3.74. Do you see it on page 89?
Yeah.
We start going, how do we solve this? It's called a second order differential equation. Okay, so to solve it, we get a solution, and that's what the solution is with the cosines and the sines. We're not going to get into that. That's a little bit too much for this class, but I want you to read through this and try to understand what is going on, and we will discuss it more next week.
And W is vertical velocity?
Yeah. So you should be able to get all the way through 93. You should be able to read that and study it and take notes on it, and you should be fine. And we will finish this up half the time on Tuesday, but I want you to start looking through the rest of the chapter. So you have the rest of the chapter in reading. It's only a few pages, but it's not going to be easy. And we're getting close to the point where I can start assigning a test. So you should be winding up on all of your assignments, all of your homework should be coming due at this point. Does that make sense to you now?
Yeah.
I think you should finish up the book, finish up this chapter. And then the real key thing are to get those problems on the worksheet.
Mm-hmm.
Those are the ones that you need to be working on. Okay, and we'll talk about that on Tuesday. Any questions? All right.
Nope.
Some of you I will see later. some of you I'll see in 15 minutes.
All right. See you on Tuesday.
Take it easy.
All right. Bye, everyone.